Ideal in AP means AP by PAP is a field. And that is contained in BP times Q BP, and also in BP divided by Q prime BP. And because this map is finite, this inclusion is finite. But if you have a finite extension of a field, it's a field again. And that means that Q B P is maximal and also Q prime BP only if I have maximal ideals, and the ring be divided out by this ideal can be a field. And so since Q is contained in Q prime, we have equality because both are maximal ideals. And that implies Q is equal to Q prime, as we wanted to show. So we saw that in a finite extension of a ring, the dimension does not change. Okay, so now we take the next approach to the dimension, which is sometimes called the Weierstrass dimension. And what's behind this is what we call Noether normalization. So you see two big names of mathematicians, Weierstrass and Emmy Noether. So there's a good story about Emmy Noether. Emmy Noether worked at the last centuries in the 20s, and she was a very good mathematician, but at that time it was very difficult for women to be successful. And then David Hilbert, also a big mathematician, tried to help her. And there was a big discussion about the mathematics community, about the men sitting over there, whether she should be included or not, and men and women should be together. And then Hilbert says mathematics is not a Bars. So in German, a Badeanstalt, so a place where people go swimming. So at that time, it was not allowed to swim together, men and women, and so Hilbert made this, and then he succeeded to get her into the mathematical community. So, okay, let me formulate a theorem. Now we have an ideal I in the polynomial ring. The claim is there exists an S smaller or equal to n and an isomorphism phi from kx1 up to kxn to ky1 up to yn, polynomial ring in the variables y, such that k xs plus 1 up to, no, not k, y, up to yn contained in k y1 up to yn divided out by phi of I is finite. And even more, if k is infinite, then the phi can be chosen as a linear map. That is a theorem. And you see here why we want to have this theorem. We have here a finite extension, and we just proved before that finite extensions preserve dimension. So the dimension of this is n minus s, because it's a polynomial ring, and so we know then the dimension of this. But I will write later on this as a corollary. So let me give a proof. So first of all, if I is a zero ideal, then of course there's nothing to do. Then we are done. So we may assume that I is not zero. And then we can take an f in I, which is different from zero, and we write the f in the following way: sum fi I from 0 to d, and with the property that Fi is 0 or Fi is homogeneous of degree I. Okay, now now I will construct the map phi in several steps using induction. So the first step is consider, and I assume that k is infinite. So if k is finite, it might be possible that you cannot find a linear map. Then it is a little bit more complicated, but not very much. But just let's see if k is finite. Then we define, let's say phi 1 of I, no, phi 1 of x1 up to xn to be m times x1 up to xn, n times. So what should I do? Phi 1 of y1 up to yn. No. So let me explain it like this. I take a matrix M and multiply it with y1 up to yn, and that should be x1 up to xn. And I want to plug in this into F. So this defines a linear map. Let's say phi 1. And then phi 1 of F is F, instead of x, I put in m times y1 up to yn. And now I do this in the decomposition into homogeneous parts. So then this is Fd. So x1 is m11 y1 comma plus m1 n yn, and xn is mn1 y1 up to mn n yn plus and so on. So if I work this out, I obtain Fd of x1 up to xn is equal, it's dangerous.
from here.
Yes?
He's fixing from here.
You can carry on.
Okay, okay.
It was not working before.
So, if we work this out, we get here fd of m11 up to mn1 y1 to the power d plus lower order terms in y1. And altogether we obtain
Here also the last 15 minutes.
sorry?
Last 15 minutes.
Okay. Altogether we obtain fd So if we choose the matrix in such a way that this does not vanish, and here we need that we have an infinite field. So we can always choose the elements m11 up to mn1 in such a way that this is different from 0. And so what we get is a polynomial in y with highest coefficients y1 to the d and a constant. And that gives me a element which gives a finite map. Now, terms of degree less than d. So that implies k y1 up to yn over phi of f k y2 up to yn is finite. And that implies k y1 up to yn divided by phi of I is finite over k y2 of n. Sorry, I think I should write here phi 1. I define it by phi 1. Is finite over phi 1 of I intersected with k y2 up to yn. And now we use induction. So maybe I will explain it then at one example. And so our famous example was k, x, y, z and the ideal was x, y, x, z. So I choose for the matrix 1, 1, 1, A, B, C, 0, 0, 0, x, y, z is I of x, y, z. So then phi of the ideal I is the ideal generated by ix squared plus xy. That is the image of the first, because x goes to x and y goes to ax plus y. The second one is bx squared plus cx y plus xz. And then if we look to these two generators, we can subtract one generator by the other one, or even not necessary. What we see is that this element, if the b is different from 0, gives me a polynomial which defines finiteness. So k, yes?
Okay, let's take the matrix here. This is a standard matrix.
So, sorry?
Matrix, you write here matrix.
So the matrix is a 1, 0, 0, A, 1, 0, B, C, 1.
So what about ABC?
ABCs are from the field, and the question is how to choose them to obtain a Noether normalization. And that's why I computed the image of the ideal, and in terms of the map it is like that. And the claim is wherever I choose A and C does not matter. I should choose B different from 0, and then it will be finite. So I should have written here A, B, C in the field K. So this is a Noether normalization. Okay, so since my time is almost finishing, I will just give some more results without proof. I will define an independent set U, a subset of X, this is X1 up to Xn, is called independent set if for an ideal I, if I intersected with Ku is 0. And the proposition K x divided by I, and the dimension of it is always greater or equal to the number of elements of U, and there exists a U such that this is equal. So, just in our example, if I is x, z, y, z, then U can be the set x and y. This is an independent set, and the number of elements is 2, and so the dimension is 2, as we saw before. Now the last thing which I would like to introduce is the Hilbert function. So I have a homogeneous idea. And then kx divided by I, which I call A, is a graded ring. So it can be written as a sum of AD and AD are the homogeneous elements of degree D. And then you have the Hilbert function hi of k is defined as the dimension over the field k of ak. So for instance, if you have a polynomial ring, if A is k, x1 up to xn, then you obtain that the Hilbert function hk x1 up to xn of k is just k plus n minus 1 over n minus 1. So that's a number of homogeneous monomials of degree k. That's okay, now the essential proposition is that there exists a polynomial HP, which is called the Hilbert polynomial, such that HP also was corresponding to the ring A of K is HA of K for K sufficiently large. So, and the thing corresponding to the dimension is that the dimension is a degree of the Hilbert polynomial. So the dimension of A minus 1 is a degree of HA. So that is another approach to the dimension. And geometrically it means a homogeneous ideal corresponds to a zero that in the projective space. And in projective space the dimension is lowered always by 1, and that's why you have this correspondence that dimension minus 1 is equal to the degree of the Hilbert polynomial. So I think I finished with the time, so thank you very much for your attention.
If you have any questions? Do you have any questions?
Yes.
Yeah.
Professor, kindly explain the last argument about its symmetric description.
What?
Last argument about this symmetric description.
Symmetric description.
Geometric description.
What I just said.
Yes, sir.
So the projective space Pn is or rather Pn minus 1, let's say, is defined as, or can be defined as the affine space An modulo an equivalence relation. So two vectors x1 up to xn are equivalent if there exists a non-zero constant lambda such that x1 that xi is equal to lambda yi for all I. So that's the dimension, the definition of a projective space. So you see, because of this equivalence relation, the dimension will go by 1. So this space has dimension n minus 1. And so the remark was, since I have a homogeneous ideal, it will define a 0z in the projective space, and the dimension is lowered, and that is the reason that in algebra the cruel dimension of A minus 1 is the degree of the Hilbert polynomial.
Sir, one question. Sir, kindly explain main difference between fluid dimension and the last Hilbert polynomial dimension.
No, there's no difference. I mean, that is exactly the equation, and we will perhaps, if there is time in the evening in the tutorial, I will talk a little bit. There is also a Hilbert-Samuel polynomial, and the same kind of theory, and the Hilbert-Samuel polynomial will have the property that the degree of A is equal to the degree of the Hilbert-Samuel polynomial.
So here dimension of A for corresponds to conventional Krull dimension?
Dimension is always Krull dimension, if I write it like this. So I started with a Krull dimension, and then I gave different approaches to it. Via Noether normalization and via Hilbert function, via independent sets. And there's something more, but I just had not enough time to explain everything.
There is a tutorial session from 3:30 to 4:30. If you have some doubts to this kind of questions, then you can discuss that with the professor later on. Thank you, Professor.
Thank you.
For your time. Now we'll have a short tea break of 30 minutes. Then we will join again in this room at what's the time? 11:25. The tea has been arranged at the end of the corridor. Please move to the corridor at the end of the corridor. Tea and come there.
So is Wi-Fi working already again?
Yes, it's working.
Great.
Better not use this. Actually, your voice is enough to reach everywhere.
Yeah.
This one gives
I
noise.
agree. Yeah. So,
It's very clear. This I would have learned this long time ago from you.
Yes, very good.
thank you. So then maybe we can change this WhatsApp.
Yes. I have already.
I can send you a
Yes,
message.
How do you add? I don't know. I didn't know how to add.
No, so you have to have my phone number, I think.
Oh, there is a QR code which we can. You can scan my QR code. I think that's easier. I never knew how to add people.